So now we talk about matrix inverses. We've made mention of them a little bit in previous videos. So now let's go deeply to talk about matrix inverses. Okay. So how do we define a matrix inverse? First of all, for a square matrix A, so you cannot find the inverse of a matrix that is not square. So, and square matrix means that the number of rows is equal to the number of columns settled. So for a square matrix A, its inverse, if it exists, it simply means that not every matrix has an inverse. Okay. So for a square matrix A, its inverse, if it exists, is a matrix denoted A raised by minus 1 such that A times A inverse is equal to A inverse A is equal to Y. So this simply means that if you multiply a matrix by its inverse, or you multiply the inverse of a matrix by the matrix, you get the identity element, the identity matrix rather. So where I is the identity matrix of the same size as A. Okay. Now, talking about the identity matrix, we considered the identity matrix under special matrices in the last video. So the identity matrix acts like the number one in multiplication, like I said. So and when you multiply something by one or multiply one by something, you get the same thing, that thing that you multiplied with. So for a 2 by 2 matrix, now the identity is 1 0 0 1. For a 3 by 3 matrix, it is 1 0 0 0 1 0 0 0 1. For 4 by 4, that will be 1 0 0 0 0 1 0 0 0 0 0 1 for 4 by 4, like that. So that's important to know. So the key idea here is that for numbers, you have 5 times 1 over 5, that's 1, you know. But for matrices, you have A times A inverse, and that will give you 1 in the sense of matrix, and 1 in the sense of matrix is the identity matrix. So we're going to see all this as we move on. So not every matrix has an inverse. I think that much has been said from the very definition that inverses, if they exist, right? So it means all matrices don't have, not all matrices have inverses. Now the question is when inverses is about the question is when do inverses exist, right? So when inverses exist, a matrix must satisfy all of the following to have an inverse. First of all, the matrix must be square, settled. So no, if you have a matrix that is maybe for a 2 by 3 matrix, no inverse. For a 3 by 2 matrix, no inverse. For a 4 by 7, no inverse. So you can only get inverses for 2 by 2, even 1 by 1. 1 by 1, the inverse of 1 by 1 is like when you deal with a number. So 1 by 1 is like you have just 5. Inverse of 5 is 1 over 5, the reciprocal. But then for a matrix, you have 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on. So you can only find the inverses of square matrices. So the matrix must be square. Inverses are defined only for n by n matrices. Non-square matrices never have inverses. So first of all, is the matrix square? If it's not square, don't even worry. It has no inverse automatically. The next thing is that the determinant must be non-zero. Now, in the last video, we said it that once another way to inspect, so if you have confirmed that a matrix is square, right, and it has so it's most likely going to have so that's not enough reason that it's going to have an inverse. Another thing is that the determinant must be non-zero, right? So, and for the determinant to be non-zero, it means that along the principal diagonal, no element there must be zero. If there's an element along the principal diagonal that is zero, the matrix is most likely does not have determinant. So a square matrix A is invertible if and only if the determinant of A is not equal to zero. So if you can find the determinant and it is not zero, then you say it is invertible. That means it has an inverse. Now, if the determinant is equal to zero, you say the matrix is singular. So a singular matrix is a matrix with determinant of zero and it has no inverse. So you say so every singular matrices are not invertible. That means they don't have inverses, right? So if the determinant of A is equal to zero, the matrix is singular and it is not invertible. Okay, so these are ways by which you can inspect. So for instance, you have this example. A is 2132. The determinant here, I think, okay, the idea of determinant is just coming up. Okay, well, I mean, maybe I should just do a brief introduction to that. Determinant of a matrix. I dealt with this in depth previous in the other playlist. So if you have a matrix A, which is say A, B, C, D, okay, the determinant of A, that's A if you like, or you can also write like that A like this, or this is my preferred one. The determinant of A is simply A times D. So the element along the principal diagonal AD multiply minus the element on the other diagonal. That's BC. That's for 2 by 2 now. That's for 2 by 2 matrix. So to take an example of that now, to take an example, so if you have a matrix, say P is 5, 7 minus 1, 3. Okay. So the determinant of P will just be 5 times 3. That's this times this. All right. Minus 7 times minus 1. That's 7 times minus 1. So the determinant of P now is 5 times 3, 15. Plus minus and minus is plus 7 times 1 is 7. So the determinant of this matrix is 22. So because it has a determinant, that means that so P is invertible. P is invertible since since that P is not equal to 0. Okay, so it has an inverse. If it has a determinant, that's for 2 by 2. Now for 3 by 3, things are a bit more complicated. All right, so for a 3 by 3 matrix, okay, I'll try to give a general form too like that, which I know is not the easiest thing to do. So you have B to be A, B, C, D, E, F, G, H, I. So to speak, so the determinant of B here, I just try to be fast about it. So first thing, you want to assign values. I mean, there are special ways to go about this, right? So this is element one. This is in row one. Okay, maybe I think it is even better to have it this way. So it's better to have it like this. A11, A12, A13, A21, A22, A23, A31, A32, and A33. Okay. So in this case now, you have to assign sign you have to assign signs either positive or negative to each element. And how do you determine that? So each element, the sign attached to each element is such that you have minus 1 raised to power the number of row plus the number of column. So I is number of row, J is number of column. So it means that for this first element now, so you say for A11, it means you have minus 1 raised to power 1 plus 1. Okay. So that will be minus 1 raised to power 2. So once the power is odd, is even. So this is going to be plus 1. So this is positive. So plus is assigned here. So for A12, so for A12, right? You have minus 1 raised by 1 plus 2. That's minus 1 raised by 3, which is, if it is odd like this, it's going to be negative 1. So this is going to carry a negative sign. And of course, 1, 3 is odd, it's even. 1 plus 3 is 4. So this is positive. So, and this is also odd now. So you can also go down. So this is also positive, negative, positive, negative, positive, negative. So once you know those signs, it's now easier to do whatever you have to do. So now with that in place, with all the signs well taken care of, based on this idea that minus 1 is raised by I plus j, where I is number of rows, and at the row position, j is column position. So to find the determinant now, you don't have to do this. So you can use any element, any row or any column. So but usually I'll just use the first row. So using the first row now, it's the sign attached to it is plus. So I'll just say plus A11. Okay, plus A11 into, and so another determinant now, a 2 by 2 determinant. So this and this, if you cross these two, so you have A22 and A23, then A32 and A32. So see this now. So this is A22, A23, A32, A33. So what I've done there is I've crossed out the row to which A11 belongs and the column to which it belongs. So I cross that out. So this can go. Now, having done that, so the next one, I have minus A12. So I have, so let me change the marker. So minus A12 now into, so A12 belongs to this column and this row. So what do you have? A21, A23, A31, A33. So that will be A21, A23, A31, A33. Okay. I have to shrink this so it can contain everything. So lastly, I go for this now. Okay, I can get rid of this. Okay. Yeah. So now the last one. Okay, this has got to go too. So the last one now is plus A13. So I have plus A13. I take the determinant. It belongs to this column and it belongs to this row. So I have this left. So A21, A22, A31, A32. So mind you, the sign is only necessary for the ones outside the bracket. So take note of that. So once you get this one out now, the next thing you can now do is, so you see, I also taking determinants of all these things. So you then have to say that uh the determinant of B now is equal to, this is positive, so A11 into, then you can take the determinant of 2 by 2, which we already did up there. So A22, A33, so this is A22, A33 minus A23, A32, like this now. Okay, so we have that. Then minus A12 into A21, A33, A21, A33 minus A23, A31. Then finally plus A13 into A21, A21, A32. So A21, A32 minus A22 minus A22, A31. Okay, so if you can figure this out, this is the determinant. So let me take an example of that. So imagine that we have a matrix Q, which is simply 1, 3, 4, 2, 1, 0, then 5, 2, minus 2. Okay, so to find the determinant here, we just say Q, the determinant of Q is equal to, again, this is plus minus plus, right? So we have plus 1 into the determinant of this, and this will go. So we have 1, 0, 2, minus 2, like this. So that goes. Then next, we have minus 3 into column and row. So we have 2, 0, 5, minus 2. So this 2, 0, 5, minus 2. So that goes. Okay. So then lastly, we have Lastly, we have plus 4. This plus 4 now. Okay, this can also go. So we have plus 4 determinant. So plus 4 belongs to this row and this column. So we have 2, 1, 5, 2. So then we can continue with the rest. So now the determinant of Q is equal to 1 into 1 times minus 2, that's minus 2, minus 2 times 0, that's 0, minus 3 into 2 times minus 2, that's minus 4, 5 times 0 is 0, plus 4 into 2 times 2 is 4, that minus 5 times 1, 5. So the determinant of Q is equal to 1 into minus 2, minus 3 into minus 4, plus 4 into minus 1. So the determinant of Q is equal to minus 2 plus 12 minus 4. Okay? 1 times minus 2, minus 3 times minus 4, that's plus 12. Then plus and minus 4. So the determinant of Q now is 12 minus 6, which is 6. So you can say since the determinant of Q is not equal to 0, so Q is invertible, meaning that it is non-singular. So that's the idea of determinant in general. So we need that concept to work here. So I mean, this, for instance, 2132 is invertible because determinant is 1. It's not equal to 0 because 2 times 2 is 4 minus 1 times 3, 3. 4 minus 3 is 1. So, and that's not 0. So this matrix has an inverse clearly. So you see that in that case now, inverse exists. Then coming to this other one, we have, this is not invertible now. You have 2, 4, 1, 2. So the determinant of B now is 2 times 2 minus 4 times 1. That's 4 minus 4, which is 0. So the determinant of B is 0. So no inverse. This is not, it is singular and it is not invertible. So a singular matrix has a determinant of 0. And then in that case, it has no inverse. Then the conceptual interpretation, a matrix is invertible if and only if, number one, its rows or columns are linearly independent. So we saw the idea of linear independence when we're solving systems of linear equations. If in the row echelon form, there's a particular row, that has all zeros, then it means that the matrix is linearly dependent. So in that case, that kind of matrix cannot have an inverse. Then the system AX equals B has a unique solution for every B. So if a system AX equals B, that's a system of linear equations has a unique solution for B, then in that case, for every B, then you can say that it's also invertible. We are going to see that as we go on. Now, the question is, how do you compute inverses? So I've explained how to find determinant, right? So to compute inverses for a two by two matrix, that's it. It's a bit easy. So for A equals A, B, C, D, the determinant of A is not zero because making sure if you once you are sure that the determinant of A is not zero, such that AD minus BC is not zero, then the inverse, A inverse is just 1 over AD minus BC into D minus B, D minus B minus CA. So it has an elaborate procedure. Um, which I don't know. There's what is called the adjustment, but since I've treated that in that matrix playlist, you can check that up right there. But for here, I'll just stick with the formula. So for a for a two by two matrix, all you just need is you need 1 over the determinant. So that's 1 over determinant AD minus BC into, so you see this D here. All right. D and A are switched, and then B and C, are not switched, but they take negative signs. So easy. 1 over the determinant into switch A and D, then change the signs of B and C. That's all. So that's how to compute for a 2 by 2 matrix. So look at the example right here now. Worked example for 2 by 2 matrix. Find the inverse of A, which is 3, 1, 5, 2. So 3 times 2, 6 minus 5, that's 1. So the determinant is not 0. So you can find the determinant. So we go, oh, okay, compute the determinant first of all. That's the first thing you do. So 3 times 2, all right, 3 times 2 minus 1 times 5, that's 6 minus 5, which is 1. Then next is apply the formula. So apply the formula now. Okay, I guess I have to go and do it because the answer is just straight here. So let's go for that now. So like we said already, okay, let me even see what the matrix looks like. That is 3, 1, 5, 2, 3, 1, 5, 2, 3, 1, 5, 2. So we're talking about inverses of matrices or inverse of a matrix. Inverses of matrices. So we said for 2 by 2, okay, if you have a matrix A, which is A, B, C, D, the inverse of A is simply this. A inverse equals 1 over the determinant, that's AD minus BC into switch A and D. So you have D here, you have A here, and then B takes the opposite sign, the negative. So just change the sign easily. So in this case, now if I want to do that for 3152, I believe, is that what it is? 3 3152, yes, 3152. So the inverse of 3152 will just be so given, okay, I guess I want to change this. Okay, let me go for this. Given R, which is 3152, find R inverse, right? So from so since R is 3, 1, 5, 2, we know that R inverse will just be 1 over the determinant of R. So that is 1 over 3 times 2 minus 5 times 1 into 3 and 2 switch. You have 2, 3 here. 1 here is minus 1, 5 here is minus 5. So that's the formula you use. So R inverse now is equal to 1 over 3 times 2, 6. 5 times 1, 5 into 2 minus 1 minus 5, 3. Okay, so that R inverse is equal to 1 over 1 into 2 into 2 minus 1 minus 5, 3. So R inverse is simply that 2 minus 1 minus 5, 3. So how do you confirm? How do you check that this is actually correct? So we can check now. Check knowing that R multiplied by R inverse or R inverse multiplied by R is always the identity matrix. So you can do that kind of check. So what's the original R? So R inverse now, the original R is 3152, if I got that right. That's 3152, yes. Then the inverse now is 2 minus 1 minus 5, 3. 2 minus 1 minus 5, 3. So if you can multiply this and you get the identity, then it means that that's correct. So what do? I have a fast way, like I said. So check the number of rows, 2 rows. So it means you're going to write each column twice. So that means you have 2 minus 5 2 minus 5. Again, minus 1, 3, minus 1, minus 1, 3. And having done that, then you can then invert this over it. 3, 1 now comes on top of this 3, 1, 3, 1. Then 5, 2, say 5, 2, 5, 2 comes on top of this 5, 2. So what do we have? This is RR inverse now. So RR inverse is equal to 2 times 3, 6. Minus 5 times 1 is 5. 6 minus 5, that's 1. Then minus 1 times 3, minus 3. 3 times 1, 3. Minus 3 plus 3, that's 0. 2 times 5, 10. Minus 5 times 2, minus 10. 10 minus 10, 0. Minus 1 times 5 is minus 5. 3 times 2, 6. 6 minus 5, 1. So you see, this identity matrix. Therefore, R inverse is actually real. So if you can put it that way. Okay. So that's, you can use formula for 2 by 2. Then that's the first, you can use that formula, right? This formula is actually derived from what is called the cofactor method for finding inverses. So which I explained in the matrix playlist, but this formula should suffice too. Then another method we can use for finding inverses. So you can expand, you can use the expansion of AA inverse equals I. What that means is that you have to assume, okay, I think I need to bring some things into this sphere. Yeah, okay. So in this case now, yeah, there are some assumptions you have to assume the inverse and then expand and then equate, as you can see. So expansion of A inverse is 1 is another method you can use. So for a square matrix A, its inverse A inverse satisfies A inverse equals I. So where I is the identity matrix of the same size, right? So the steps you need to take, you assume a symbolic inverse. Suppose A is n by n, let A inverse be. So you just assume the inverse to be something where each xij is unknown, like you don't know any of these things because you are looking for the inverse. So once you have that in place, the next thing you then want to do is you can then multiply A with A inverse. So compute A inverse. So the A you know and the A inverse you don't know. So compute that as a matrix multiplication. So this gives a matrix whose elements are linear combinations of the known Sij. Then the next thing is you want to compare with the identity matrix. So you now compare the expansion you have with the identity matrix. So since AA inverse is equal to Y, each element in the product must match the corresponding element of the identity matrix. So AA inverse IJ will be equal to IJ such that you have 1 where I is equal to J and 0 where I is not equal to J. So this gives a system of linear equations in the unknowns Xij. And then you can solve the equation. So solve the system of equations to find all entries Xij of A inverse. So this one has been done, right? This one has been done for 2314. But I think I've got so okay, I'll just go through this and I'll now go back. The matrix, the inverse I found before. I'm not going to use this method to find that inverse again. So you can see how it works for the same thing. So take a 2 by 2 matrix, say A is 2314. So assume the inverse is A inverse. So now you're assuming the inverse to be XYZW. So multiply A by A inverse. So A inverse is 2314 multiplied by XYZW. So you have XZ twice multiplied by 2, 3. So you have 2x plus 3z here. And here you have um x plus 4z. Here you have 2y plus 3w. That's 2 times 2, 3 multiplied by yw. That's 2 times y plus 3 times w. Then for the other one, you have 1, 4 multiplied by this. That's y plus 4w. So at the end of the day, so this one is a 2 by 2 matrix. So you can then compare it with I to the identity matrix 2 by 2. That's 1, 0. So it means that 2x plus 3z is 1, 2y plus 3w is 0, x plus 4z is 0, y plus 4w is 1. Okay, so this system gives the set of equations here. So 2x plus 3z is 1, 2y plus 3w is 0, x plus 4z is 0, then y plus 4w is 1. Then you solve for the unknowns. Solve simultaneous equations here and there. So like you can solve 2x plus 3z equals 1 with x plus 4z together using elimination. We dealt with such methods in previous videos. You can solve 2y plus 3w together with y plus 4w. So if you go through all that process, you end up getting the inverse, which is 4 over 5 minus 3 over 5 minus 1 over 5, 2 over 5. So you can then check that AA inverse is equal to I. So this method works for any square matrix, though the number of equations grows with matrix size. So if you have bigger matrices, this is not recommended, but you should know that this is a method. So I'm going to use this same method to find the inverse of the R I did before, right? So R here, because the determinant is 1, it's a bit easier to handle, but you don't always expect easy ones like this. So 3152, right? So we want to find, so to find R inverse for R, which is 3152, using using the expansion of R, R inverse equals I. Okay, so I'll just go ahead and do that now. So so we can say let R inverse be equal to R1, R2, R3, or what can I say here? So R1, R2. Okay, let me just say R11. Okay, R11, R12, R21, R22. I don't have to make it this complicated, but let me choose it this way. So because we don't know the inverse, so we are looking for these elements. So once we get these elements, we have found R inverse. So we now have that R inverse is equal to 3152 into R11. Okay, let me even do it together. Uh, so, so RR1 equals I implies that, so 3152, which is R, right? 3152. Okay, okay, 3152. So I've made it so big. So this implies now this implies that we have 3152 into R11, R12, R21, R22 equals the identity element for 2 by 2. That's 1001. Okay, that's what we have for that. So next thing now, because we have two rows here, we write each column twice. So we have R11, R21, R11, R21. Then this is R12, R22. R12, R22. Then we put this 3, 1, we put it over the first row generally. So we have 3, 1, 3, 1. Then next we have 5, 2. So 5, 2 over the second row. So this is 5, 2, 5, 2. So all this now is equal to 1001. Okay. So next we can tidy things up. So here we have 3R11 plus R21. Then this is 3R12 plus R22. Then down here, we have 5R11 plus 2R21. Here we have 5 5R12 plus 2R22. Okay, 5R11 plus 2R21 plus 5R12 plus 2R22 equals 1001, right? So, I hope everything is fine. Yeah, I think so. 3R12 plus R22, then 5R11 plus. So it's better you use single numbers that will not be confusing like this, but it's okay. So what we are doing next is to then compare term by term. So now we know that this is equal to this. So we can write that as this is 311 plus R21 equals 1. Okay. I like to call that equation 1. Then so there's another R11, R21 somewhere, right? R11, R21. So this is another R11, R21. This now is equal to 0. So we have 5R11 plus 2R21 equals 0. Call that equation 2. So then we can split that now. And then we have the other set. We have 3R12 plus R22 equals 0. So this is equal to this. Then call that equation 3. So this is equation 3. Then finally, you have this 5R12 plus 2R22, okay, equals 1. This one here. So call that equation 4. So you have 4 equations and you can solve them for the variables they have in common. So we can solve 1 and 2 together and 3 and 4 together so we can solve this for R12, R11, R21. So what do we do? Clearly, the coefficient here is 2, the one here is 1. So we can multiply, we can say equation 1 multiplied by 2. Okay, so we have 6R11 plus 2R21 equals 2 times 1 is 2. Okay, then equation 2 can remain the same. So equation 2 multiplied by 1. So we have 5R11 plus 2R21 equals 0. So what can we do now? Because these two have the same coefficient, we can then subtract. Okay, so we can subtract. So subtracting now 6R11 minus 5R11 is 1R11, which is simply R11. So 2R21 minus 2R21 is simply 0. Okay, so this will just cancel out. And this is equal to 2 minus 0, that is 2. So clearly R11 is equal to 2. Now that we have R11, we can then substitute that into equation 1 or 2, anyone you choose. So substitute, substitute substitute into equation 1. So if we substitute into equation 1, we have 3R11 plus R21 plus R21 equals 1. So R11 is 2, so we have 3 times 2 plus R21 equals 1. So the 3 times 2 is 6 plus R21 equals 1. So that means that R21 is equal to 1 minus 6. So R21 is equal to minus 5. So we have got R21 here like this. Now we go to the other side and also solve for the other element we have there. So here now, I think we can do the same thing. R22 has coefficient of 1. This one has coefficient of 2. So we can also do the elimination thing. So here we say equation 3 multiplied by 2. So that is 2 times 3 is 6R12 plus 2R22 equals 2 times 0 is 0. Then equation 4 times 1, it remains the same. So we have 5R12 plus 2R22 equals 1. So we can then subtract again because they have the same signs. They are both positive. So we can subtract. If you add different signs, we can add. So 6R12 minus 5R12 is R12. Then 2R22 cancels 2R22. So 0 times 0 minus 1 is minus 1. So R12, all right, R12 is minus 1. So it's this one is easier because they don't contain fractions. Then now that we have this, now we can then say substitute into equation 3. Substitute into equation 3. So equation 3 is 3R12 to R22 equals 0. 3R12 plus R22 equals 0. We got R12 to be minus 1. So we have 3 into minus 1 plus R22 equals 0. So we have minus 3 plus R22 equals 0. So R22 is equal to 3. So we have all the elements. We can then say, so R inverse is equal to, of course, R11, R12, R21, R22, and that is equal to, what is R11? R11, we got that to be 2. Then R12, we got that to be minus 1 here. Then R21 is minus 5. Then R22 is 3. I think that actually works. 2 minus 1 minus 5, 3. That was the same R inverse we got in the first case. 2 minus 1 minus 5, 3. Exactly. So this also works. So it depends on what anything you choose. So this is the same R inverse. So if you have fractions, you have to be more careful to not make mistakes. So that's what exactly has been done here. So that's method 2. Method 3 now is the row reduction or what we call the Gaussian elimination form. So in this case now, okay, I think I need to tidy this up a little bit. Okay, this can go clearly. Okay, so method 3, row reduction or Gaussian elimination. This method works for any size square matrix. Now, this is most preferred if you have very large matrices. This is better, like you just do row reduction. And of course, it can be confusing, but I've explained row reduction in the previous video. So you want to check that out. I also have it in the initial matrix playlist. So this method works for any size square matrix. Steps to do, you write the augmented matrix. Now, I also explain how to do augmented matrix a lot. So you have A and you augment that now. So this one is slightly different. So you have the matrix A, whose inverse you're looking for, and then you have the unit matrix of the same order. Then you use row operations to turn A into I. So you have to make sure that A becomes I. So once A becomes I, by doing the same operation with I, automatically I becomes the inverse. That's what row operation does. So you can use row operations to turn A into I. So the right side becomes automatically A inverse. So for a 2 by 2 matrix, okay, I'm going to explain this. Then I'll now go back to the worksheet and do the same thing with the same matrix. So you can see that you can use different methods to find the inverse for that matrix. So imagine a 2 by 2 matrix. You want to find the inverse of 1, 2, 3, 4. So you form the augmented matrix 1, 2, 3, 4, and then you augment it with the initial, with the unit matrix 1, 0, 0, 1. So what do? The goal is you want to make this one look like this at the end of the day. So by the time you have succeeded in making this one look like this by carrying out row operations on all the elements, then whatever this one becomes at the end of the day will now be the inverse, as you are going to discover. So what do? This one is already one, so no problem. So you just need to make this one into three, into zero. So how do you make that into zero? So it's row two. So the new row two now is going to be old row two minus three times old row one. If you remember, if you check the row echelon form thing I did all of this. So you just write this on 1210 normal. Then for this now you have 3 minus 3 times 1. That'll be 0. Then 4 minus 3 times 1. That's 4 times 3. 4 times 3 times 4 minus 3 times 2. That's 4 minus 6, which is minus 2. Here you have 0 minus 3 times 1. That's minus 3. Here you have 1 minus 3 times 0. That's still 1. So your goal has been achieved here. Next thing now you want this one you want this this particular one to be 1 now. And the way to make this 1 is to multiply by minus half. So the new row 2 is going to be the minus half times this old row 2. So it means row 1 is going to remain 1, 2, 1, 0 like this. If you don't understand, don't worry. I'm going to do it over on the worksheet, so step by step, so you get what I'm talking about. So you have 0 minus 2. So we need this to be 1, right? So multiply row 2 by minus half. So it means row 1 will be what it is, 1, 2, 1, 0. So you have 0. So 0 times minus half, 0. Minus 2 times minus half, that's 1. Minus 3 times minus half, that's 3 over 2. 1 times minus half, that's minus 1 over 2. That goes. So the next thing you want to do is this 2 now has to become 0. And the way to do that is you can just say 2 minus 2 times 1. So that's the old row 1 minus the 2 minus 2 times the old row 2. That's what's going to happen there. So you eliminate this 0 now. So you have 1, 0. So here now you have 1 minus 2 times 0, 0. Then this 2 minus 2 times 1, that's 0 up here. Then this 1 now minus 2 times 3 over 2. That's 1 minus 2 times 3 over 2 is 3. So 1 minus 3 is minus 2 right here. Then you have 0, uh, 0 minus 2 times half. So that's 0, right? 0 minus 2 times R2. So that's 0 minus, what's happening here? So 0 minus 2 times this. That'll be 0 minus 1. So I think this should be actually minus 1. It looks like something is wrong here. Or is it me? Okay, this is 3 over 2 minus this. So R1, this is 0, 0 minus 2 times R2 minus 0 minus 2 times R2 is actually 1. So I think this should be minus 1. This should be some kind of minus 1. But it's okay. Like I'll do the real thing on the worksheet using the same matrix I've been using. That 3152 now using a row echelon form. So all right. So the question again is to find, I guess I want to change markers now. I want to see new colors. Say I want to see mm, okay, I'm spoiled for choice. Maybe this. So to find to find the inverse, to find the inverse of R, which is 3152, okay, using Gaussian elimination. Gaussian elimination. Okay, elimination. Okay, what do? We form the augmented matrix. So we have 3152. Augment it with the unit matrix in the same dimension 1001. Okay. So now This is the matrix R. This is the unit matrix. So we want to transform it into at the end of the day, we now have matrix. We have unit matrix here, and then we automatically have R inverse on this other side by the time we are done with all the transformations. So that's the goal. So let's go step by step. So first step now, we need this to be one. We also need this to be one. So maybe we can do those two immediately, right? Because you may want to be fast about some of these things. So we can do those two immediately, so we don't waste time. So this is R1 now, and this is R2. So what's going to happen is that the new R1 is going to be the new R1 is going to be 1 over 3 of the old R1. Okay, so you multiply this through by 1 over 3 so that you can get this to be 1. Then, of course, the new R2 is now going to be 1 over 2 of the old R2 so that you can get this one to be 1. So to do that now, we have 3 times 1 over 3 as 1. Then this is 1 over 3 here. You augment. This is 1 over 3. This is 0, like that. This is 0 here. Then for this one now, you're multiplying by half or you're dividing by 2. Well, multiplying by 1 over 3 is like dividing by 3, right? 3 over 3 is 1. 1 over 3 is 1 over 3. 1 over 3 again. So here, 5 over 2, 5 divided by 2, or 5 times half, that's 5 over 2. Then 2 divided by 2, that's 1. Then 0 times half is 0. Then half times 1 is half. So that's one step. So the next thing we want to do now is to make sure that these two, okay, we want to make sure that these two become 0. But to avoid confusion, I'll do it one by one. We could have done the same thing, the two at once, but let's do it one by one. Okay, I think it's better to do it one by one generally, right? So let's do it one by one. So now I want to take this to be 0. So how do I do this? So now, this is a old row 1, old row 2 now for relative to the new one. So the new R1 now is going to be the same. It's going to be R1. Nothing changes. So we have 1, 1 over 3, then 1 over 3, 0. Nothing has changed. But row 2 is going to change. So for row 2 now, because we want this to be 0, so it has to be the old row 2 minus 2, the old row 2 minus 5 over 2 of the old row 1. So because now this is 5 over 2. So that will now be like for this 5 over 2 minus 5 over 2 times 1. Okay? So that's 5 over 2 minus 5 over 2. And that's simply 0 here. Okay? Next one, you have 1 minus 5 over 2 times 1 over 3. So you see, 1 minus 5 over 2 times 1 over 3. So we need to do some maths. That's 1 minus 5 over 6, I think. Yeah. So the LCM is 6. 1 and 6 is 6 minus 6 and 6, 1. That's 5. So that's going to be 1 over 6 right here. So here we have 1 over 6. Okay. Then for this also, it's going to be 0 minus 5 over 2 times 1 over 3. Okay. So that'll be 0 minus 5 over 10. So that's simply going to be, no, this is um 0 minus 5 over 2 into 1 over 3. Did I say 5 over 10? No. So 0 minus 5 over 2 times 1 over 3. So that'll be minus 5 over 6, not 5 over 10. Minus 5 over 6. Then lastly, I have half minus 5 over 2 into 0. Of course, this is 0, so the answer, this just remains half. So I have half here. Okay. Um, Maybe I was too fast in trying to make this one 1 before. I didn't have to waste my time like that, but it's okay. So now this one has got to be 1 again. So maybe I should have just made this one 1 first, eliminate this and go step by step. So if you want to do yours, don't waste your energy. So next thing now, I need this one to be 1, right? So R1 remains what it is. R1 is R1. So I have 1, 1 over 3, 1 over 3, 0. Then R2 now will now be 6 times the old R2 so that this one can become 1. So we have 0 times 6, 0. 1 over 6 times 6, 1. Minus 5 over 6 times 6, that's minus 5. 6 times 1 over 2, that's 3. So finally, we have to work on this one. So 1 over 3 now has to become 0. So how does that happen? So the new R1 is going to be, um, okay, so Okay, we are going to work on that R1, but let's do R2 first. R2 is going to remain R2 because we already have what it should be. This is, we need 0 here. So 1001 is what we need. So this 139 is the problem left. So to do that, what we just do is we say R1 minus 1 over 3 times R2. Okay, because that's the way we can say minus, that's 1 over 3 minus 1 over 3 times 1. That'll be 0. So this is what's happening. So for this now, of course, we can write this 0, 1. Okay, minus 5, 3. Okay, but for this one now, R1, that's 1 minus 1 over 3 times this 0 down here. So that's 1 minus 0, which is simply 1 here. So the 1 remains here. For this one now, we have 1 over 3 minus 1 over 3 times 1. 1 over 3 times 1 is 1 over 3. So that will give us the 0 we need. So this becomes 0 now. So we have achieved that, but it has to translate to this place. So R1 is 1 over 3 minus 1 over 3 times, that's this 1 over 3 now, minus 1 over 3 times minus 5. Okay, that's like 1 over 3. That's like 1 over 3. 1 over 3 minus 5 over 3, right? Yeah, 1 over 3 minus 5 over 3. Is that correct? That's or even plus. So this 1 over 3 minus 1 over 3 times minus 5. That's 1 over 3 plus 5 over 3. 1 over 3 plus 5 over 3. That's 6 over 3, which is 2. Okay? So this now is 2. So we get 2 right here. Then coming here now, we have R1. That's 0 minus 1 over 3 times this 3. 0 minus 1 over 3 times 3. 1 over 3 times 3 is 1. But wait, that's 0 minus 1, which is minus 1. Minus 1. So with this, now that you have got, once you can verify that once you can verify that this is the unit matrix, automatically this has got to be the inverse of R. So we can say, so R inverse is equal to 2 minus 1. That's 2 minus 1 minus 5, 3. So if it has fractions, you have to be more careful. And that is correct because that's the same thing we've been getting. So 2 minus 1 minus 5, 3. So using all the three methods, we keep getting the same 2 minus 1 minus 5, 3 like this. So the initial method we used also, we got 2 minus 1 minus 5, 3 also. This 2 minus 1 minus 5, 3. So uh, Gaussian elimination keeps giving us, so all the three methods definitely give us the same result. So with that, we are done with that. So now, we go for inverses, inverse versus solving systems of linear equations. So you can solve the system of linear equations using inverses. So consider a system AX equals B. So of course, A is the matrix of the coefficients, while X are the variables, and B will be the right-hand side. So method A, using the inverse. Oh, so if A inverse exists, you can then say X is equal to A inverse B. So example, imagine that you have 2x plus y equals 5 and x plus y equals 3. So the step one is A now is 2, 2, 1, 1, 1, the coefficients of the variables, and B is 5, 3. So of course your x, this x now will just be x and y. So here now you want to find the inverse. So the first thing is the determinant is 2 times 1 minus 1, that's 1. The inverse now will just be switch 2 and 1. So you have 1 and 2, and change the sign of 1 and 1. So you have minus 1 minus 1. So that's the inverse of this matrix. So if you then multiply, so your solution now A will now be A inverse B. So the inverse multiplied by 5, 3, the right-hand side. So if you do that, that's 1 times 5, 5, minus 1 times 5, 5, minus 1 times 3, 3. So 5 minus 3 is 2. Then minus 1 times 5, that's 5 also. 2 times 3, that's minus 5. 2 times 3 is 6. Minus 5 plus 6, that will give you this 1. So we can solve systems like that. Yeah. So maybe I'll do an example when I see the questions, the practice. So method B is row reduction, so which is preferred in practice. So instead of computing A inverse, you can solve A A augmented with B. So the advantages here is that this is faster and it is more numerically stable, and it works even when inverse does not exist. So you can do Gaussian elimination too. So by the time it's all done, so you can get the possible solutions you should get in that case. Um, Maybe I need to demonstrate 2x plus y, 2x plus y, x plus y, 2x plus y equals 5, x plus y equals 3. Okay. 2x plus y. So solving equations now. Solving equations using inverses. Okay, we have 2x plus y equals 5, then x plus y equals 3. That's what that is talking about. So that has been done. Computing inverse was done here, but now I want to just use the row reduction method to show that we can actually get solutions there too. So this now in matrix form, you can just that can be rewritten as 2, 1, 1, 1 into x 2, 1, 1, 1 into xy equals 5, 3. Okay, so this is why you say this is ax equals b now. Okay, so uh next we could talk about the augmented matrix. So this is augmented matrix now. Augmented matrix following that will be, you write, this will be 2, 1, 1, 1. So this is 2, 1, 1, 1 augmented with 5, 3 like this. So this is AB. So the goal is you want to transform this to become, so this one becomes the identity matrix using Gaussian elimination. And by the time that is done, you end up getting the the values of X here by the time you do the transformation. So let's go for that. So 2, 1, 1, 1, 5, 3. So 2, 1, 1, 1 augmented with 5, 3. So what's the first thing we do? So the first thing to be done here is to I guess I'm missing one of these colors. Okay, yeah, let me just continue with this. So the next thing to be done here now is to do the row Gaussian elimination and turn this one to unit matrix like I've described previously. So, and one by the time we do that, then we'd have got what we need to get like that. So I'm going to do that in a jiffy. So, okay, so now we need this one. So I won't make the mistake I made before. We need this one to be 1, right? So this is row 1, this is row 2. So what do? We say the new row 1 is going to be half of the old row 1, so that this one can be 1 at least. So in that case now we have 2, or row 1 divided by 2, 2 divided by 2, that's 1, 1 divided by 2, that's 1 over 2. Then 5 divided by 2, that's 5 over 2. We have this. Then for row 2 remains row 2 for now. So we have 1, 1, 3 right here. So what's the next thing we need to do? We need to make this one 0. And because they are both 1, it's easy to handle. So what's going to happen next is we now have row 1 remains row 1 because that's not going to change. So we have 1, 1 over 2, then 5 over 2 right there. So the next thing is row 2, where the work is. Row 2 is simply going to be the old row 2 minus the old row 1 because they are both 1. So 1 minus 1, 0. 1 minus half, that's half. This 1 minus this half now, that's half. Then 3 minus 5 over 2. So 3 is 6 over 2. So 6 over 2 minus 5 over 2 is also half, right? Yeah, 3 minus 5 over 2 is 1 over 2. So what's the next thing we need to do? This guy has got to be 1, okay? So for that to be 1, we multiply through by 2. So R1 remains for now. So R1 remains R1. So we have 1, 1 over 2, 5 over 2. But then R2 now is the old new R2 is going to be 2 times the old R2. So 2 times 0 is 0, 2 times half is 1, then 2 times half again is 1. So we have that. So the next goal is to make this one 0. So what do we do to make that happen? So now R2 remains what it is. R2 is R2. So we have 0, 1, 1 for R2. Well, R1 now is going to change. So R1 is going to be old R1 minus half times old R2. So that will be here now 1 minus half times 0. That's 1 minus half times 0. So half times 0 is 0. So 1 minus 0 is simply 1. Then this is half minus half times 1. Okay? This half minus half times 1. So that's half minus half. And that will be the 0 we expect it to be. And lastly, We need this one. We do the same here. So that will be 5 over 2 minus half times 1. So that's 5 over 2 minus 2 over minus 1 over 2. That's 4 over 2, and that's simply 2, like this. So with this now, we can just read off the answers. So we can then say x is equal to 2 and y is equal to 1. That's that kind of thing. So this is normally we could have just solved this one directly, but I needed to demonstrate with something simple. So you see, at the end of the day, the answer is 2 and 1, like we said. So x is 2 and y is 1, just like what we have from Gaussian elimination method like this. Okay, so we can solve equations using inverses or using row reduction, which is, so if this matrix is so large, it's better to go the row reduction route so that you don't keep wasting time trying to look for inverse. So if you have like 5 by 5, it's better to use row reduction than to look for inverse. But although that can be tedious too, but just, if once you're careful, you'll be fine. So comparing now, so let's compare the three methods. So the method, inverse method, what are the pros? It is a direct formula and it is elegant. The only problem is that it is slow for large systems and it requires invertible matrix. So if the matrix doesn't have a determinant, you can't even use that. The expansion method, it is systematic and it is good for small matrices. But it is tedious for larger matrices because you have to get all the elements. Imagine if it is a 5 by 5 matrix, you have to find 25 elements to be able to get the inverse. That's a lot. But for small matrices like maybe 2 by 2, 3 by 3 you can still manage, but 3 by 3 is already getting tedious too. Row reduction is efficient and it is general. The constraint is that it is less compact and can be error prone by hand. So if you are doing row reduction, it be a different sign can cause problem. A number changed, something like that can be really tedious. So, but if you are careful, row reduction is the best way to go. So the important rule is that never compute an inverse just to solve a system unless explicitly asked. So if you are told to solve a system, look for simpler ways, except you have it is compulsory to use a particular method. Okay. So you can easily use row reduction instead of computing inverse. So, or you can even do intuition. Like the last problem I solved, it's very easy. You can just, by inspection, you can even know the answer. Just multiply something, subtract, and get your answers. But when things become really tedious, then these methods become useful. So, key takeaways. An inverse is a matrix version of a reciprocal. We've said that much. So, inverse is like reciprocal of numbers. Only square matrices with non-zero determinants are invertible. So, if non-zero determinant it makes a matrix invertible, that is, it has an inverse. A inverse undoes the effect of A. That means if you multiply A inverse by A or A by A inverse, you get the identity. Then row reduction is the most practical way to compute inverses. We've said that already, and I've also demonstrated it. That was the last example here using row reduction. So as far as you can be careful, you get the correct answer. Then inverses give insight into existence and uniqueness of solutions, right? So inverses give you existence. So if a matrix has inverse, tells you that you can have it has solutions. If not, um, if an equation if the matrix of coefficients of of a system of equations has inverse, that tells you the system has solutions. All right, so we have practice problems as usual, 10 of them. Okay, I guess I need to do it in fives because this is looking too scanty here. Okay, this is 1 to 6 first of all. So for each problem, determine if the matrix is invertible. If it is, compute the inverse. For system problems, solve using A inverse B if possible. Okay, look at this. Now, is this invertible? 1 times 5, 5. 5 minus 6, minus 1. So this is invertible because that's the determinant of minus 1. 4 times 1, minus 2 times 2, 0. So this is not invertible. So you cannot compute the inverse. 2 times 6 is 12. 12 minus 12, not invertible. 0 minus 1, that's 1. This one is invertible. The determinant is 1. Then here, okay, well, until you have to compute this one manually to be sure. And I already explained how to find the determinant in this case, right? So you want to try that out. Maybe I'll take one problem of 8, 9, and 10. Let's see. Solve the system using inverse if possible. Then solve the system using the inverse if possible. Solve the system using the inverse if possible. So once you have a 3 by 3 system like this, it's getting too tedious. I'm not even sure if I should embark on this journey because I've spent an hour already. Maybe I should stop here so you can just look at the methods, the kind of the one I did and follow that to solve this. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much. If you haven't subscribed, what are you waiting for? Subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Okay, you can also become a member of the channel by clicking on join. That gives some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Try your hands on the questions if you think you can't solve any. So just let me know. So I may make a separate video to do that. Bye.